Lecture 3, Influence of Ionic Strength on Reaction Rates. This is true for moderate concentrations, and this theory is due to Bronsted-Bjerrum, Christensen, and Scatchard. Again, let us consider our reaction A plus B giving you an intermediate complex X, which then disintegrates to give you the products. In this particular case, X is not necessarily an activated complex, but can be regarded as such in this context. The rate of reaction is dependent on the concentration and not activity of the complex because it is a dilute solution. So we can look at rate V as being equal to K dashed into capital X. This is equation Roman numeral 8. Now the equilibrium between the complex X and reactants A and B is again given by the activity of X divided by activities of A and B, which will be equal to XFX all over A times B times FA times FB. That's equation number 9. If we substitute in for X in equation 8 by using equation 9, we get the velocity V being equal to K naught times the concentration of A and B times the activity coefficients of FA, FB divided by Fx. Remember that V over concentration of A times concentration of B is actually equal to Ke. Now if we substitute and then take logs, we obtain log the base 10 of Ke being equal to log the base 10 of K naught plus log the base 10 of Fa plus log the base 10 of Fb minus log the base 10 of Fx. Compare this with the equation Roman numeral 4. However, according to Debye and Haeckel's theory, which relates activity coefficient with the valency and oxidation states of Z and the ionic strength, it gives that I is given by log of base 10 of F is equal to minus capital Q Z squared, the square root of I, where Q is equal to 2 pi times N all to the 1/2 times E cubed all over 2.303 eta kt all to the 3/2 times 1000 to the 1/2. Here, eta is the dielectric constant of the medium, and the ionic strength is defined from Lewis as I is equal to 1/2 the sum of Zi squared Ci, where Ci is the concentration of the ion. If we substitute equation X into equation 1V or equation 10 into equation 4, and log K is equal to log K naught plus log Fa plus log Fb minus log Fx becomes log Ke is equal to log K naught minus Q root I all into Z squared A plus Z squared B minus open bracket ZA plus ZB all squared. If we sort out the algebra here, we find that log of K naught plus 2 capital QZ AZB root I will be equal to log Ke. It is found that for aqueous solutions at 298 K, capital Q is about 0.51. Hence, the equation now becomes log K is equal to log K naught plus 1.02 ZAZB root I. Now, how do we test the validity of this equation? What we do is we study the rate of reactions in media of varying ionic strength I, plot log Ke over K0 against square root of I. This should give us a straight line of slope 1.02 ZA ZB. If ZA or ZB is not, then Ke is not a function of I. A good example of this is the base catalyzed hydrolysis of ethyl ethanoate, which has a zero gradient. If ZA is positive and ZB is positive, then the rate constant is increased. For example, CONH3 all into 5 Br++ plus Hg++. Here, ZAZB is equal to 4. The gradient is positive. For ZA equals to +2 and ZB equals to -1, ZAZB becomes -2, and here the rate constant is decreased. As an example, again, CONH3 into 5 Br2 plus OH minus, here ZAZB is equal to -2. And the rest of this can be seen in the figure below.